Previously we looked at exponential growth, and we looked at a differential equation that we can use to solve for exponential growth. And one of the applications that we talked about for exponential growth could be a population of something, whether it's an animal or people or bacteria in a petri dish. The problem with that model with exponential growth is that it's unlimited. It assumes that the population can grow and grow and grow, and it's not going to be slowed down or capped at any maximum level. To be more realistic, a petri dish or the earth or an environment can only hold a certain number of organisms. And so that environment is going to have what's called a carrying capacity. And we get a slightly different differential equation to model a what's called a logistic differential equation. In this case, the growth rate, or the rate of change of a population, that's what the capital P stands for, is not only proportional to the population itself, but it's also proportional to how close it is to its maximum population or its carrying capacity. And so this differential equation is more appropriate for modeling populations, because those populations are going to be limited by resources or space, and so there's a maximum carrying capacity of an environment. So let's take a moment here to look at how we would solve this particular differential equation. It is a separable differential equation. Since k and m are both constants, m representing the carrying capacity, which is the maximum population, and k representing a growth constant, the larger the k, the faster the growth is going to be. Then we want to integrate this with respect to p, because p is the only variable that we're going to have here, p representing the population. Since this is a growth with respect to time, that's why we have the differential t here, and so at some point we should have a t involved in our equation. So separating the variables, we end up with 1 over p times the quantity m minus p times dp is equal to our growth constant k times dt. And then we're going to integrate both sides, and when we integrate here, we're going to have to use partial fraction decomposition. To use the partial fraction decomposition here, we have to figure out what 1 over p times m minus p is going to be as separate fractions. And it turns out that the numerator on both of these is going to be the reciprocal of our carrying capacity. It's going to be 1 over m. So rewriting this expression then, we want to integrate 1 over m divided by p plus 1 over m divided by m minus p, keeping in mind that p is a variable and m is a constant. At this point, since m is a constant, we can factor the 1 over m out from both of these terms here in front of the integral. And actually we can multiply both sides by m, that carrying capacity now, and write it over on the other side. Making a couple of other changes real quick, we can factor out the constant k, so we're just integrating dt, or 1 times dt, on the right side. We make this solution a little bit easier now. So we have the natural log of the absolute value of p plus the natural log of the absolute value of m minus p. Now, since p here is negative, we actually have to remember the chain rule here, and if we were to be strict about this, we might use substitution, and since the derivative of m minus p is going to be negative 1 dp, we need to change the sign here. So using the chain rule, essentially this plus is going to change to a minus, and that's going to equal mk times the integral of dt, which is t, and that's going to be plus our constant of integration. Now, for simplicity in solving later, I'm going to multiply everything by negative 1. That's going to allow us to solve for p a little bit more simply later. So what we end up with then, combining our natural logs, is the natural log of m minus p over p. It's the absolute value of that. I'm sorry. So we have here the absolute value of m minus p. I had that wrong there. It was p minus m. M minus p divided by p equals negative m, which is a constant, times k, which is a constant, times t, which is a variable, time, minus some constant c. To get Well, to keep in mind here, we need to keep in mind here that our population is going to be positive. So the absolute value on this p down here is really pointless because that's always going to be positive. But also our maximum population minus our current population always has to be positive also, because our carrying capacity is always going to be greater than the population. So we can get rid of these absolute values here, and that makes solving for p a lot easier. We can exponentiate both sides now, and we get m minus p over p equals the exponent e to the negative mkt minus c, and that's the same thing as saying e to the negative c times e to the mkt, the negative or the opposite of mkt. And keep in mind here that this e to the negative c is itself a constant, so we're going to replace that with our own constant, and this a here is going to depend on a few things, but depends mostly on our initial conditions. So then we end up with m minus p equals p times a to the a times e to the negative mkt. To get p by itself here, we'll go ahead and add p to both sides and then factor it out, and we get m equals p times that quantity. And one more step here, fairly straightforward at this point. To get p by itself, we get the population is equal to the carrying capacity divided by 1 plus a, which is it depends on our initial conditions there, times e to the opposite of mkt. Keep in mind that m here and m here, those are the carrying capacity. K is a constant that depends, that shows us how fast the population is growing. It's called the growth constant. And then a is going to depend on our initial conditions, and we can solve for that given an initial condition. Here's what the slope field for this type of differential equation would look like. It has the features that we would expect for such a situation. With a low population here along the y-axis, when we have a low population, the growth is not going to be very steep. It's going to be a small positive growth. And then as the population increases to a certain point, then the growth of the population also increases. Once it increases past half of its maximum or carrying capacity, then the growth starts to decrease again, as we would expect, because resources are starting to deplete, we're starting to run out of room, and as we get closer and closer to this carrying capacity, in this case the carrying capacity is 100, as we get closer and closer to this, it starts to approach it, and it's never, the graph of a population here is never actually going to reach 100, but it's going to be an asymptotic function and get close to it. So if we started with an initial condition here, or initial population of, say, 5, now this may represent 5 of some sort of organism, 5 bacterium, or maybe 5,000 or 5 million. We're not really sure how this is scaled here, and that would depend obviously on what we're looking at, what type of organism we're looking at. But if we take this initial condition and plug it into the solution that we got, we would get an equation that looks like this. And again, this equation is what we would expect here. We start out with slow population growth, and as the population grows, the rate of growth increases until we get halfway into the carrying capacity, and then it starts to level out again. And we can see here it never quite gets to 100, but it gets really, really close. So here's what the general logistic equation looks like. It comes from the differential equation. It looks like this, where it says the growth of a population with respect to time is proportional not only to the population itself, but to how close it is to its carrying capacity. And we get this equation here that the population is equal to this, where k is a growth constant, which tells us how fast the population has the capability of growing, and this capital M here is the carrying capacity, or the maximum population in the particular environment.